Hi, thanks for joining me today. I'm going to be going over problem 2 from week 1 of the Summer Invariants puzzle competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find out more details about the competition. Anyway, this is the problem I have for today, and it looks a bit long, but if you want, pause video, or I'll leave a link in the, I'll leave a full description of the problem in the description down below as well, but I'll quickly read it out and then we'll get stuck into a solution. So we have Alice chooses a sequence of n terms from the set 1 up to k. So n could be bigger than k, it could be less than k, it could be equal to k. It doesn't really matter. So they're allowed to be repeats in this sequence because it's a sequence and not a set. Now Bob then guesses guesses a sequence of n terms from 1 up to k. So he guesses a sequence, and hopefully it's a match of something similar to what Alice has. He'll make a guess. He can then make plenty more other guesses as well. And here's how the game works. Alice will receive Bob's guess, and in response, Alice will tell Bob the number which is most common among all the terms guessed correctly, choosing the highest digits if there's a draw, or just saying k if there are no matches. So here the order does matter. The order of the sequence does matter. So up to here, I've given a bit of an example up here. So suppose Alice's code was 12231, so in that order. And then Bob was to guess 33221. Well, then the 3 here doesn't match up with this one. This 3 here doesn't match with this 2. This 2 does match with this 2. So there's 1, 2 in the correct position. This 2 doesn't match with this 3, but this 1 does match with this 1. So the 1 matches as well. So there's 1, 1 in the correct position and 1, 2 in the correct position. So we have a draw. So Alice is going to respond with the higher digit, which is 2. So in this case, Alice would respond by saying 2. So this is a setup. So perhaps take a moment to digest exactly how this kind of game works. And then the problem we have, or two problems, A and B. Part A, we want to know for what pairs nk does there exist a Q such that Bob can know Alice's sequence after Q guesses. So Bob can make plenty of guesses, and then Alice will respond. And we want to know for what pairs of values n and k is it possible that there exists a number Q such that Bob can guarantee to know Alice's sequence in just Q guesses. That's part A, and then part B says that for such nk, i.e. for the nk that is your answer in part A, we want to show that Q is of order nk. So in other words, we can work out we can work out what Alice's code is in just of order nk guesses. So this notation here just means there exists some positive constant c such that Q is less than or equal to c times nk. So in other words, we can guess Alice's code, or Bob can guess Alice's sequence of numbers after just at most cnk guesses. Anyway, this is the problem. If you want, pause the video and have a read of it, or have a read of the problem in the description. I'm going to stop waffling and get stuck into a solution. Okay, so I claim that the solution to part A is given by this set here. So in other words, for any pairs nk, there exists a Q if and only if nk is in this set here. So what is this set? It's a set of nk where k does not equal 2, and hopefully it's quite clear to see that this set here contains almost all pairs nk, it doesn't include the ones where k equals 2. And when k does equal 2, there's one special exception where n equals 1. So I claim that these guys here are the pairs that work. There exists some Q, obviously dependent on n and k, such that we can guess, or Bob can guess Alice's sequence in just Q, in at most Q guesses. So why is this true? Let's deal with the kind of easy cases first. So let's deal with this guy here. So if n equals 1 and k equals 2, well, because k equals 2, then that means that Alice's code, or Alice's sequence, is just going to contain, and because n equals 1 as well, Alice's code is either going to be 1 or it's going to be 2. So case 1, Alice's code is just 1, or I should just write 1. And case 2, Alice's code is 2. And then what we're going to do, or what Bob's going to do, is he's going to guess 1. Now, if it is the case that Alice's code is 1, so case 1, well, he's guessed 1, Alice's code is 1, so there's exactly one match. So Alice, and that match is with the digit 1. So Alice is going to respond by saying 1. Case 2, if Alice's sequence is actually just 2, well then there are going to be 0 matches. So remember, the rule for that is that Alice will then respond by saying k. And in this case, k is equal to 2. So Alice will then just say 2. So we've got two different cases here, and we're able to distinguish, because they kind of have different outcomes, we can then work back and therefore work out whether it's case 1 or case 2. So in just one guess, we're able to work out what Alice's sequence is. Cool. So that's this kind of case here. Now we want to work with this set here. So we're kind of just worried about when k equals 2. So let's look at when k is less than 2 first. This is another easy case. So when k is less than 2, well, k must therefore be 1. So if k equals 1, well then Alice's code, we know immediately. We don't even need to guess. It's just going to be 1, 1, 1. So it's just going to have, it's going to be a sequence of n ones, and we're done. So that's going to be the case where k equals 1. And now I'm going to leave the case k is bigger than 3 for now, and we'll actually look at that more in part B. The last thing I want to do for part A is just prove that we can't do it for n bigger than 1 and k equals 2. So in other words, when k equals 2, and ignoring this special case here, we can't find a q. And then, as I say, when we look at k is bigger than 3, we'll actually just do that in part B and show that we can, there exists some q, or q is of order nk, and then we'll be done. So the next thing I want to do is prove that we can't do it for k equals 2 and n being strictly bigger than 1. But let me clean up the whiteboard first. Okay, so let's suppose that n is bigger than 1 and k equals 2. And now the issue with this is we want to prove that Bob it's impossible for Bob to get Alice's code even after millions and millions of guesses. And the essential issue is that Bob can work out perhaps a number of 1s and 2s in Alice's sequence. However, he's not going to be able to work out the order in which they occur. And remember, order is important in this problem. So let's kind of prove that that's the case. Let's suppose Bob makes a query, and that query is going to contain 1s and 2s, and it's going to be n digits long. And let's suppose it has a 2s in and b 1s, and of course, therefore, b would be n minus a. And let's suppose Alice's secret code, which obviously Bob doesn't know, let's suppose it contains n minus m 2s, and therefore m 1s. And now let's define c to be the constant, which is the number of instances where Bob's code has a 2, but in that same position, Alice has a 1. So in other words, we could write out Bob's n-digit sequence, and then Alice's actual n-digit sequence, or secret sequence underneath, and C here counts the number of times where, in a position, Bob has written 2, but Alice has written 1, and we kind of read across the sequence. So C is going to be somewhere between 0 and n. Cool? Now, first question is, how many 2s has Bob predicted correctly? How many 2s are in the right position? Well, it's simply going to be A, the number of 2s he guessed, minus the ones which are in a wrong position. And the only way you can be in a wrong position is if Alice has guessed a 1. So the number of 2s in the correct position, which, I don't know, let's call it correct underscore 2, is going to be A minus C. And what is correct underscore 1, or subscript 1, i.e. the number of 1s in the correct position? Well, it's simply going to be M minus C, because M here is a number of 1s in Alice's code, and we can kind of split that up into the 1s guessed correctly and the 1s guessed incorrectly, and we know there are precisely C that Bob guesses incorrectly, so where Alice has 1 but Bob has guessed 2, therefore there must be M minus C where Bob has guessed 1 and Alice has a 1. So we have correct 2 is A minus C, and correct 1 is M minus C. Now, remember, Bob is going to make this query, and then Alice is going to respond by either saying 1 or 2. If Alice says 1, so if Alice says 1, well, what does that mean? Well, that means that the number of correct 1s is going to be bigger than the number of correct 2s. So that tells us that M minus C is bigger than A minus C. And if Alice says 2, which is the only other option, we either have no matches whatsoever, in which case these are both 0, or we have that this guy here is bigger than this guy here, or bigger than or equal to this guy here, because remember, if it's a draw, then we're choosing the higher digit, i.e. 2, and notice that all those cases there are equivalent to A minus C being bigger than or equal to M minus C. Okay, so let's just quickly go over that. If Alice responds by saying 1, then we know that the number of correct 1s must be strictly bigger than the number of correct 2s, and if Alice responds by saying 2 either, there are no matches, Bob hasn't got any of the positions correct, in which case Alice is by default going to spit out K, and K in this case is 2, or it's the case that the number of correct guesses for the digit 2 that Bob has is bigger than or equal to the number of correct digits 1 that Bob has guessed. So we have this case or this case here, and so essentially if Alice, whatever Alice says, 1 or 2, all it's going to tell us is if A minus C is bigger than or equal to M minus C. And obviously this inequality here is equivalent to A being bigger than or equal to M. So when Bob makes a query, the only piece of information we're able to extrapolate based off of Alice's response is whether this inequality here is true or not. But what is this inequality here saying? A here is just the number of 2's in Bob's guess, and M is just the number of 1's in Alice's actual guess. So I guess we could perhaps rearrange this and say that, well, M we know is just N minus, A is just N minus B, perhaps. So we can have a play with this, and all we're going to do is look at the number of 1's that Bob has guessed, and then this inequality, whether we know it's true or not, is only going to tell us the number of 1's that Bob has and the number of 1's that Alice has, and whether or not the number of 1's that Bob has guessed is less than what Alice actually has, or if it's more than. So that might not have made any sense. I was a bit waffling there. Let me repeat that. We do all this stuff, Alice says a response, and based off of it, we're going to get whether this inequality here is true or not. Is A bigger than or equal to M? Either that's a true inequality or it's a false inequality. And based off of what Alice says, we'll be able to know if this is true or not. But that's not enough information, because that's just going to tell us whether or not the number of 2's that Bob has guessed is bigger than or equal to the number of 1's that Alice has guessed. And it goes back to that thing that I was saying, that yes, we can use this, we can do a few different queries with different values of A and work out perhaps what the value of A is, so the number of 2's in in Alice's code, but we're not going to get any information about the position of these 1's and 2's. So the only, I guess, possible way that we'd be able to know Alice's code for sure is if, it was a sequence of all 1's or all 2's or something like that. But because n is strictly bigger than 1, we know it's not going to be, or it's not necessarily a constant sequence. It could be that, it's 1, 2 or 2, 1 or something like that. In which case, we have no hope for knowing exactly what Alice's code is. We can simply get the number of 2's and the number of 1's. Anyway, I was waffling a lot there. Hopefully that has all made sense. Let's move on to the case where k is bigger than 3. Okay, so now suppose that k is at least 3. Now what we want to do is generate a sequence which is absolutely wrong, such that there are no matches with Alice's code. Because then once we can do that, we can kind of alter each digit one by one and then check if there are any discrepancies in what Alice says. And if there is a discrepancy, then we'll know that there's something interesting happening with that position and that digit that we've kind of queried. Anyway, how can we work towards getting a code which is absolutely wrong? And I guess one thing you might think about is how comes we couldn't do that in the case where k equals 2? So have that question in the back of your mind, but let me go and try and work towards getting a code or a sequence which is absolutely wrong, i.e. there are 0 matches with Alice's code whatsoever. So Bob can guess each of these n codes here. So the first one is just all 1's. The second one is with a 2 at the front and then all 1's. The third one is with a 2, 2, and then all 1's, and so on, all the way down till we have one with all 2's. And there are clearly going to be n different guesses here, or I guess actually n plus 1 guesses, because the number of 2's goes from 0, 1, 2, all the way up to n, like so. So there are n plus 1 guesses there, and Bob's going to ask each of these. And for now, assume that Alice responds by saying either 1 or 2 to each of these, because either Alice can respond by saying 1, or Alice can respond by saying 2, or if there are no matches with, say, this code and Alice's code, so this particular one and Alice's code, then Alice is going to respond by saying k. So either Alice can say 1, 2, or k. Now, if Alice says k, so say here, so she says, say 1 here, but then says k for this code here, well, then that means that this code here has no matches with Alice's code, and that's exactly what we want for the first part, to get a code which has no matches. So then we'll be done. But so I guess now assume that that doesn't happen, i.e. she doesn't say k for any of them. So for each of these guys, she says either 1 or 2. Now hopefully it's quite clear to see that if she's going to say 1 or 2 for all of them, she's going to have to start by saying 1 for this one, because there's no way she can say 2 for this, because there's no 2's in it at all. So either there's a 1 in her code, in which case she says 1, or there's not a 1 in her code, in which case she says k, which is at least 3 and not 2. So we have 1 here, and here, it could either be 1, or if there are no 1's in the code, but there is a 2 at the start, then she would say 2, but let's just assume it's 1, and so on. And notice that the last one here, she's definitely going to have to say 2 to, because she's not saying k, and there's no 1 in it, so she can't say 1, so it's got to be 2. And this kind of sequence here of these what Alice responds as we go across is actually going to be a non-decreasing sequence. I.e., it's always going to be ones, and then at one point it's going to hit 2, and then it's going to continue on. And I'll let you kind of check for yourself to see why that's the case. But it's essentially going from one to the next. If there is a change in going from here to here, how's it going to become? Where's that change coming from? Well, say it's here to here. So let's say this one here did spit out a 2. Say going from here to here, what's the only difference? Well, we've gone from starting 2, 1 and now going 2, 2. So the difference is in this second digit. So going from here to here, 1 to 2. So either going from here to here, we've reduced the number of ones. So the number of potential matches for ones has decreased. But also the number of potential matches for 2 has increased because we've increased the number of 2s in our sequence. Anyway, this guy here is going to be 1, 1, 1, and then it's going to end up being 2. And at some point, it's going to change. So let's suppose it changes at the sequence S1 and then changes at sequence S2. So in other words, S1 is going to be a bunch of 2s, say, and then a 2 here. And let's say this position is the alpha position, and then the next one is going to be 1, and so on. And at this point here, Alice responds by saying 1. But then with this one here, when we have the next 2, so this would, if we look at this kind of sequence of sequences, this guy here would be the sequence after this guy here. So it's when we put a 2 in the next position. So this is the alpha plus 1 position, and then it'd be a 1, and then so on. Then Alice will say 2 to this guy here. So we know that this is going to happen because of this sequence of the numbers 1, 1, 1, 1. It's eventually going to hit 2, and at some point, that some point is going to be here. So S1 and S2 is what we're going to label these guys here to be. So to get here, all we've done so far is made n different guesses. So that's quite nice, or n plus 1 guesses, I guess, because this thing here is certainly order nk, which is what we want. Now we've got to this guy here. We have a sequence S1, which is a bunch of 2s and then 1s, and then S2, which is a bunch of 2s and then one more 2, and then the rest 1s. And Alice says 1 to this guy, and then says 2 to this guy. Well, that means in this position here, so in the alpha plus 1th position of Alice's code, we know that there is a 1 or a 2. How do we know that? Well, let's suppose that there wasn't a 1 or a 2 in the alpha plus 1th position. If there wasn't a 1 or a 2, well then, let's say it was a 3 in the alpha plus 1 position. Going from, so let's say Alice's code was something, 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 and then 3 here, and then something, something, something. Going from here to here, S1 to S2, these codes are exactly the same, except in this position here. So for Alice to say 2 different numbers, kind of backtracking, must mean that there is a difference, that the difference coming between these 2 numbers is coming from these 2 numbers. So there must be, one of these digits here must be in position alpha plus 1 to cause this discrepancy here. So there must be a 1 or a 2 in this position here. So we couldn't have a 3 here, for example. So we know that in the alpha plus 1th position, there is a 1 or a 2. And now what we can do is introduce the sequence, which is going to be, so we're going to take S2, we're going to look at S1, and then every single 1 in this sequence, we can change to a 2. So take S1, and then take each 1 by one. So perhaps we'll start by taking this last one, and we're going to replace it with a 2. And then what we're going to do is query this. So ask Alice if this is her code. And then if she responds by saying 1, then we know that this digit here is neither a 1 or a 2. Because if it was a 1, if this digit here was a 1, then when we change it to a 2, well, we've decreased the number of 1s that there are that like matching with Alice's code and this kind of guess code. So that would mean that she'd respond by saying 2, but she hasn't done. And if it was a 2 in there, as opposed to a 1, then we've increased the number of 2s in this sequence going from S1. So that means that she'd respond by saying 2, because now there's one more match with the 2s matching than there are 1s matching. So hopefully that makes sense. Let me just put this back to 1. So essentially what we're doing with S1 is we're taking each of the 1s, so there are, n minus alpha, I think, 1s there. And what we're going to do is do n minus alpha different queries, and with each one we're going to choose a different one and change it to a 2. And then what we're going to do is depending on what Alice says, if she says a 2 now in response to that, then we know that in that position where we've changed the 1, so in the example I gave, I changed this last one to a 2. If Alice then responds by saying 2 to that, then we know that this last position here is either a 1 or a 2. We don't know which one it is, but we know for sure it's a 1 or a 2. So we do that with each of these n minus alpha 1s, taking them out and swapping them for 2s, and that's going to take n minus alpha guesses. And what we'll be able to work out is in these n minus alpha last positions, which of those positions have either a 1 or a 2 in. But we won't be able to distinguish whether it is a 1 or it is a 2, but we'll know for sure which positions have either a 1 or a 2 in. And now we can do something very similar with S2, except now what we're going to do is look at these first alpha positions and take out the 2s and replace them with 1s. And then, let's say we take this 2 out and replace it with a 1. Alice will either respond with 2 or 1. If she responds with 1, then we know that this guy here is either a 1 or a 2, again, by the exact same kind of reverse argument, because either that is a 1, in which case we've increased the number of matches with 1, hence why Alice has changed to 1, or this guy here is a 2, and we've kind of now taken it away, so we've reduced the number of 2s by 1. So if Alice responds a 1, then we know that the digit that we've changed to a 1 must be a 1 or a 2, and if she says 2 in response, then we know that digit there is a 2. Is neither a 1 nor a 2. So hopefully that's made sense. Perhaps pause the video and try and convince yourself that that's true. It's a little bit difficult to explain with just whiteboard, but essentially what Bob will do is he'll take each of these n minus alpha last 1s, he'll then one by one flip them for 2s and make n minus alpha different guesses, each with one of the 1s chosen flipped to a 2, and then depending on what Alice says, he can work out whether that chosen digit that he's flipped is a 1 or a 2, or it's something else. Okay, and similarly for S2, we can look at the first alpha positions and take out 1 by 1, make alpha different guesses, and take out these 2 1 by 1s, and get rid of the 2 and replace it with a 1, and then we'll know if that position there is a 1 or a 2. So once we've done this will take, again, n guesses. So this will take n guesses. Once we've done this whole process, we'll be able to get a sequence of n digits, and what we'll know each position here, we can tell you, yes, this is supposed to be a 1 or a 2, or no, it's not supposed to be. So we won't know what the digits are in Alice's code just yet, but we can say, yeah, this one here is a 1 or a 2, this one isn't, but we don't know what it is. This one isn't, say this one is a 1 or a 2, and let's say this one is a 1 or a 2, and that one isn't. But again, the ones which are 1 or 2, we don't know if they are 1 or if they are 2. All we know for now is that they are 1 or 2. Anyway, I hope that has made sense. Let me clean up the whiteboard and we'll continue. Okay, so now we have a sequence of n terms where we can with confidence say that Alice's code does have a 1 or a 2 in the first position, it does have a 1 or a 2 in the second position, and we know for sure it doesn't have a 1 or a 2 in the third position, and so on all the way up to the last position. And to get here has taken at most n plus 1 plus n, so 2n plus 1 guesses, and that's certainly of order nk. So we're happy up to now that it's taken, we've got a code here. And remember, for this first part, what we want to do is get a code which we know is 100% wrong. It has 0 matches. And we've got to this stage here. So what we can do now is just look at this code here, which is in the positions where we know it's a 1 or a 2, we're going to put 3. And this is, I guess, is kind of why the case gets different when you have k at least 3, because you now have like a dummy digit you can use. So 3 is definitely not there, and 3 is definitely not there, and 1 is definitely not there, because if it was, then that would have a circle around it. Okay, so you can kind of do this. So wherever there's a circle, you're putting a 3, and wherever there's no circle, you're putting a 1, and we're going to call this code here W, and we know W is completely wrong. If we were to query W, if we were to ask Alice, is this your code? She'd respond by saying K, because there are 0 matches. And remember what I said before when we had the kind of the Bob's initial guesses of 1 1 1 1 1, 2 1 1 1 1 1, 2 2 1 1 1 1 1, and so on. We assumed that all of those Alice responded by saying 1 or 2, and if she didn't, she'd respond by saying K, in which case we know that that particular code had 0 matches. Then we could just use that as our code W. So we just want a code which has 0 matches, which is what we've got so far, and it's taken at most 2n plus 1 guesses. Now what we're going to do is let Wij be equal to W but with ith position replaced with j. Okay, now what does this tell us? So well, I here is between 1 and n, because there are n positions, and j here is between 1 and k. Now, if we change the ith position to a j, so I guess if we use this example, what we have up here, W of 1, 7, say, we'll just change one of these digits in this wrong code. So it would change the I here is 1, so the first position, so this guy, to a 7, and then the rest would remain the same, like so. And so we've only made one change. So if we split this into to Alice, and she responds by saying 7, then we know that there's a match with the 7 there. Unless, I guess one thing I should worry about is what if k equals 7? What we're going to do is start from j equals 1. So we're going to start by putting j equals 1 in here. And then at some point, if Alice doesn't say k for each one, because if she says k for each one, then we know that, so if we plug in j equals 1 here, and Alice responds by saying k, then we know that that first digit isn't a 1. Cool. If we plug in j equals 2, and then Alice responds by saying k, then we know that isn't a 2. And I guess in this case, that would be impossible because we know this first digit is a 1 or a 2. But just for argument's sake, suppose she said k when we plug in j equals 2. Then what if we plug in j equals 3? What does Alice say? Well, she'll say k. But then this kind of process will continue. And whilst you check all the j's from 1 up to k, at some point she might say j in response. Because we know the rest of this guy here has 0 matches. Because we know this guy here has 0 matches. So this thing here having 0 matches means that if, when we try all the different values of j, starting from 1 upwards, if there is a change in Alice's response, because most of the time she's going to say k, because k minus 1 times for the j, this is not going to be a match, and hence she will respond by saying k. However, if it is the case that this first digit here is one of the numbers 1 up to k minus 1, then when we plug in that corresponding value of j, so let's say this first digit is actually a 4, say, then when we plug in j equals 4, Alice is going to respond by saying 4. The only issue is, what if this first digit here is a k? Because she's going to respond to k all the time if this is not to match. But then I guess if she responds k to absolutely each and every value of j, so j equals 1, j equals 2, all the way up to k minus 1, and including k as well, then we know that there's a k in this first position. Because if it wasn't a k, it has to be something else. It has to be a 1 up to k minus 1. But then when she said j, when we plugged in j, so if j was 4, as I say, when we say 4, she'd respond by saying 4. But because she said k for all the first k minus 1 entries, we know that that guy there is a k. So that's going to take at most k guesses to get this first digit. It's going to take at most k guesses to get this second digit, and so on all the way up to this last digit. So it's going to take at most nk guesses from once we have a completely incorrect code to getting to here. We know it's going to take at most nk guesses to get Alice's code correctly. And of course, we can perhaps reduce this number a bit because we know, this number here we knew was a 1 or a 2, so we only need to check j equals 1. And then if it's not 1, then we know it must be 2. So we can save a little bit there, but we know for sure that this thing here, once we get here, is going to take at most nk guesses. And then if we add that onto the 2n plus 1 we had before, this guy here is going to take at most nk plus 2n plus 1, and that guy there is certainly of order nk. And that solves the problem. Anyway, I hope you have enjoyed this video. I apologize, it's one of those difficult ones to make on a whiteboard, but hopefully if you haven't managed to wrap your head around particular parts of this video, do just grab some pen and paper and convince yourself that what I've said is indeed true. Anyway, thank you for watching. If this is your first time at the channel, thanks for watching the video, but also do check out some of my other solution videos and some of my other maths videos as well. They might interest you too, and do consider subscribing if you haven't already. I'm almost at 2,500 subscribers, which should be huge. Anyway, I'm just going to stop waffling now. Thank you for watching. I'll catch you in the next one. Have a great day.